Hi everyone. Today I'm going to talk about the BERT paper. Don't worry, I'm recording myself, so ignore the thing. So BERT is also a language model which revolutionized NLP. It got published in 2018, just a couple of months after the model, the GPT-1 model from OpenAI, and it again was a new state-of-the-art language model, and I'm gonna talk about how it actually works. And a small fun fact, Google likes to use Muppets of Sesame Street to name their models. But yeah. Okay, so to motivate this, I'm gonna show you an example we use every day. So this is just, I Googled this 2 days ago. If you Google something like what is BERT, often comes like a paragraph referencing to a web page, and the important thing is here, it gets marked the answer. So you type a question and the answer is gonna be marked inside a paragraph. That's one of many tasks BERT can perform, and I'm gonna explain how it works in detail later. So a bit about the background. So in NLP, it's all about words, sentences, languages, and we want to mathematically describe them. So how do we describe sentence word? We have already seen this in the previous presentations. We want to create word embeddings or token embeddings. So for example, you have a word dog and you convert it to a vector in some embedding space. But the problem is many words have different meanings. So for example, if I say I have a meeting on this date, date refers to the day. And if I say I have a date with this girl, this means that I meet a romantic kind of meeting, you know what I mean. So yeah, it's all about representing context. So we want to create word or token embeddings which captures context as good as possible. And I'm gonna talk about the history a bit. So first we had recurrent neural networks. This is a machine learning model which processes inputs one token at a time and carrying the hidden state token per token. So for example, here you have, for example, the sequence token X, and you predict it, and each prediction is depending on the previous state. You have seen it already, I'm not gonna explain it more in detail, but the problems here are difficulty learning long-range dependencies, and it only goes into one direction, because if you look at a sentence, you always want to look into both directions to capture the full context. I will talk this. This is very important. I'm gonna mention this later in more detail. And lastly, it's sequential, so it's very slow and doesn't scale well. Next, we have long short-term memory, LSTMs. This is like an advancement of recurrent neural networks, and it introduces a functionality which just helps those tokens to remember what is important and what is not important for input, forget, and output gates. And we have still a problem that is sequential and it just goes into one direction. Then we have the first big improvement. This was also a model proposed by Google called Elmo, and this was one of the first groundbreaking models which contextualized left to right and right to left context embeddings. So you have two independent architectures, both compute their embeddings in the embedding space, and what you then do is just concatenate them, okay? So this was already a big improvement, but the problem is that it's still sequential. And then the very big groundbreaking thing came, transformers and attention got introduced, and this changed everything. So as you already seen, it's not sequential anymore. We can compute the attention, because attention tries to capture context as good as possible, and it's the most important thing. It's parallelizable and very good scalable. So I'm not gonna explain attention in detail because we have already done this, but here's a good graphic which showcases it. The animal didn't cross the street because it was too tired. This tries to capture the context of all those words, and as you can see, the animal is the most important word which it refers to. Then we have the OpenAI GPT model, which we just heard half an hour ago. So from the encoder and decoder architecture, GPT uses only the decoder part. So why is that? Because the main objective of GPT was actually to generate text. And you can imagine encoder and decoder as like encoder actually learns the context, and the decoder tries to get this context and map it to, for example, generating new words. I would even argue that GPT isn't so good in even learning the language. It's more about generating text and what we humans want to see when we generate text, that it makes sense. And yeah, as I said, it's based only on the transformer decoder. And another very important thing GPT is implementing is the fine-tuning approach. So as we heard in the previous presentation, we have two types of training. We have the pre-training and the fine-tuning. And the pre-training and fine-tuning approaches are very important to solve actually specific tasks we want to perform, because in the end we all want to perform tasks. And here, GPT was one of the first models which implemented a very good fine-tune approach, but previously they were feature-based approaches. And what is that? So in feature-based approaches, we create word embeddings on a pre-trained model, but actually those embeddings are then fed into another architecture which does the task for us. So we need to kind of two different architectures to perform a task. And this doesn't scale very well. So in the fine-tuning approach, you pre-train the model on like a base objective. When you pre-train, this is actually the model tries to understand the language, and then you fine-tune it on the same model, but with another specific tasks you want to perform. And this is very groundbreaking because this is very more scalable, and you don't rely on different architectures. And also pre-training, this is the real training. This goes over days. So for example, BERT got trained in, like, for example, 1 week, and the fine-tuning only takes a couple of hours. So I also implemented some BERT models, and you can just use the weights initialized from Google on GitHub, for example, and then use your own data set to perform your own tasks. And this went, I only trained my BERT model in 30 minutes or something, and it performed very well. So yeah. Now let's look at previous problems, which previous methods incorporated. First, we have the GPT model, and this only incorporates unidirectional context. So it only looks from left to right. And this is okay for text generation, but as I said, for a model to actually understand the language, because you look at a sentence from left to right and right to left, we want to have a bidirectional context. Elmo, for example, uses left to right and right to left, but independently, and then concatenates that. It was already a good approach, but not good enough, and BERT is trying to tackle this as well. And the second problem is that many models require additional task-specific engineering, so are not implementing the fine-tune approach. And GPT was, for example, one of the groundbreaking fine-tuning models, and BERT also wants to have this approach. And then with those two things together, we get BERT. BERT stands for bidirectional encoder representation from transformers. Bidirectional means bidirectional context with self-attention. Encoder it only uses the encoder component of the transformer. Representations means just word embeddings. And transformers is because the BERT architecture is still based on the transformer architecture. Yes. So a few key aspects of BERT. So BERT is a sequence-to-sequence language model. This means the input is a sequence of tokens or words, and it outputs the same sequence just embedded in the context. BERT is pre-trained using bidirectional transformer encoders. We're gonna look at the pre-training process more in detail, and can be fine-tuned for specific downstream tasks. So this is the quick, most important aspects of BERT. So let's look at the pre-training task. BERT is trained on two base tasks: masked language modeling. In the next slide, we're gonna look at this in more detail, but this ensures bidirectional context, and I'll explain why. And this masked language model concept is very important because this is the main task where BERT actually captures token level meanings. And then the next tasks it trains on is the next sentence predictions. So this is more about if you have many sentences or paragraphs, it tries to get the relationship, learn the relationship between those sentences. And this ensures sentence level like information and context. And then you compute two different losses and then just combine them. Okay? So let's look at it in more detail. We want to look at masked language modeling. So why is that? Because if we have the bidirectional context, my colleagues already mentioned it, that model can actually cheat. So for example, if you have like this, for example, like a GPT model, it produces the new token based on what they've seen. So this is the start of token, and it should predict open because open is the first word. And then if the input is the start token and the open token, we want to predict A. So in order for the text generation to work effectively, you mask the attention mechanism so it can only look in one direction. But to implement bidirectional context, we don't want to mask the attention. We want that it looks into two directions, and this graphic explains pretty well. But as I said, the model can cheat. It can just look up the word and doesn't learn anything. So this is where masked language modeling comes in place. Let's see how it works. Pre-training task 1 is masked language modeling, and the key thing is to mask K% of the input words. BERT uses 15% because this seems like a good threshold, and then you predict the masked words. So for example, we have as an input, I'm studying computer science, and then you mask them. Random words, and for example, studying and science, and then the model tries to predict the words on a vocabulary probability distribution. Okay, so this is the first task, and this masking process is randomly, and this is the key concept of BERT, how it trains bidirectionality. Because with this, all the words or all the tokens can see each other, but when it's masked, it doesn't help it. So it needs to understand the language still. Okay, let's look at the second task. This is very easy. Next sentence prediction, given two sentences A and B, does B follow A? So for example, sentence A is I'm studying computer science, B is I specialize in machine learning, and BERT tries to predict whether B follows sentence A, like strictly follows. And in this example, for example, it is true. So let's look at the BERT architecture more in detail. What is the input and what is the output? The input is a pair of sentences. Why do I say sentences? Because in the pre-training process, these are really sentences, because you want to train if sentence B follows sentence A. But when you fine-tune it, so you want to train it on specific tasks, the pair of sentences can be anything. So the first sentence can be like a question, and the second sentence, or rather saying sequence, can be a paragraph. So when I refer to sentences, I mean actually sequences, but for the pre-training process, it's just sentences. And then you feed the input into a stack of layers from the encoders, from the encoder architecture, from the transformers. And then you output the probability distributions over all the tokens. So as you can see, this is the transformer architecture. This is the encoder part, and this is the decoder part. GPT, for example, only uses decoder part, and BERT only uses the encoder part. And as you can see, it's literally nearly the same. They just used it and stacked like 12 layers of this encoder component. And yeah, I will not dive more into the details because my colleagues already explained it very well, but to sum it up, first you create the input and embeddings, then the positional encodings with the cosine and sine function. Then you go into a multi-head attention block, add those add norms, feed forward layers, again residual connection and normalize it. And then the most important part is the last linear layer, because this last linear layer depends on the specific task you want to fine-tune it on. And in the end, you generate output probabilities. This is the specific input representation BERT uses. So first are the yellow tokens here. This is the base embeddings for those words or tokens without any context. The next thing is it adds a segment embedding indicating whether sentence A follows sentence B. I mean whether, in this example, my dog is cute, corresponds to the A embedding, so it corresponds to the first sentence, and he likes playing corresponds to the second sentence, so it's marked as B. And then you have the positional embeddings like in the vanilla transformer architecture. And we have one very important token here. This is the CLS token. This token is always pre-appended on every input, and this stands for classification. And in the pre-training process, this classification tokens outputs whether sentence B follows sentence A. And for the future fine-tuning task, this classification token can mean anything, any kind of classification. And why does, the important question is, why is it pre-pendant before the input? Because it can look at the whole sentence. So it captures the whole context or the whole meaning of the whole sentence, and that's why it's is pre-pendant, exactly. A quick diagram of the attention mechanism again. So as you can see, OpenAI GPT only looks from left to right. So all those transformer blocks calculate their self-attention from left to right. But BERT calculates also from left to right and right to left simultaneously. That's also the important part. Not independently, but rather simultaneously. This diagram shows the pre-training process very general. So you have sentence A, prepended classification token, and sentence B. Then you have then you compute the initial input embeddings. These are all the encoder layers, and then you have the output tokens, which are finally embedded. And then how the model learns is it computes the next sentence prediction and the masked language modeling losses. So I'm gonna show an example here. So here we have the initial input in words. I'm studying computer science. I specialize in machine learning. The next thing is it's gonna be tokenized. So we add this classification token and another token which separates the sentences. And yeah, those words are now inside a vector. What then is done is it's masking random words of the sentence and marks whether this sentence belongs to A and this sentence belongs to B. This is in blue and red. Then it goes through the BERT encoder architecture, and we get the final embedding. So these are already contextualized embeddings, and now we can use those embeddings, for example, to fine-tune it or feed it to another task. But in the pre-training process, you feed the classification token to one independent linear layer, which has two output features, indicating whether sentence B follows sentence A. And then for each mask token, there is also a linear layer, and the output size is, of course, the size of the whole vocabulary, also again, a probability distribution around this. Let's go to the fine-tuning. So, as already mentioned, you initialize the model with the pre-trained model weights. This is already done, and you fine-tune it for a specific task. How do you fine-tune this? Is you add a linear layer in the end of the transformer blocks, and you train it again from end to end. And you can really take any other kind of data, which is a sequence-to-sequence model architecture, and you can train this on a specific task. I'm going to show you two examples: sentiment analysis and question answering. Sentiment analysis is indicating whether a sentence gives like a positive feeling or a negative feeling. For example, if you have reviews of a movies or a restaurant, it can say if the review is bad or good. And the next task is question answering. So this is what we've seen in the motivation slides. When you ask something in the Google engine, for example, it answers the span of the answer in the paragraph. So for the sentiment analysis, as you can see, it's still the same architecture. We use the inputs, but as you can see, here is just one sentence. So you may ask, I thought BERT has always two sentences. Yeah, it's true, but you can leave it empty, and empty is still an element in this sense, and that's why it works. And then you can train it on just one sentence, and you only look at the classification token again. And that's why the classification token is so important, because it captures the whole meaning of the whole input. Next, we have the question answering. So again, we have the input. Here it says now two sentences, but those sentences are, the first sentence is a question, and the second sentence or the sequence is a whole paragraph. And now we don't look at the classification token because it's not a classification task anymore. We look at where in the paragraph is the specific answer. And then for each token in this paragraph, you have a classification whether it is the start or the end token. And this is very nice because, as I said, BERT is very flexible and can learn a lot of special NLP tasks.
Sorry, we are already like at 25 minutes.
Oh.
So
Okay, so this is just mentioning that language modeling is very important. Here are some evaluation benchmarks that it outperforms, for example, GPT and every other model in many different NLP tasks. Here's another saying that even outperforms humans. And yeah, let's go directly to the Q&A.